we're going to do a little review today for exam 3, chapter 7, chapter 8. Let's see here. Small cursor. If I wanted to use that cursor for any pointing, wouldn't be much help. So give me a second. Nope, it's not there. Personally. Mouse pointer, stop it. Let's make it bigger. There we go. Okay, so the printout, unfortunately, is not in color, but you should be able to see wherever I had it yellow, it should be kind of grayed out along on the numbers. So those are the ones we're going to look at today. All right, so number 1. In which of the following groupings are the 3 terms closely related? Okay, so I guess we have to look at each one in turn. Let's see, what terms are we dealing with? Kinetic energy, energy of motion, same thing. Cohesive forces, okay. Cohesive forces, potential energy, attraction, which is cohesive forces. I'm trying to mess you up with different terminology. Disruptive forces. Okay. Potential energy, electrostatic interactions. And cohesive forces. Okay, so it looks to me like we need to correlate kinetic energy and potential energy with other terms that influence the phase of matter. So kinetic energy is associated with disruptive forces. Potential energy is associated with cohesive forces or attractive forces, the same thing. So let's see, kinetic energy, energy of motion, cohesive forces. Nope. That belongs with potential energy. How about potential energy, energy of traction, disruptive forces? Nope, that's kinetic energy. Kinetic energy, electrostatic, disruptive. Well, electrostatic interactions could be anything. So I discount that one because it doesn't even fit. I mean, it's not specific enough. Let me put it that way. Potential energy, electrostatic interactions, and cohesive. Okay, the potential and the cohesive are right. Electrostatic interactions, that's a matter of interpretation. I think what the author of this question is looking for is electrostatic interactions are attractive forces. But I mean, what if you have 2 identical charges? 2 positives that blow each other apart. So in this case, pick the best answer. And that's D. That's what I get for using a test bank. Okay, let's see if I can do this. Those 2. Turn that off. Okay, number 2. The phase is particles close together and held in fixed positions and completely fills the container, apply respectively to. Okay, so I think we're dealing with one type of phase here and a different type of phase here. So where are the particles close together and held in fixed positions? That's a solid, right? And completely fills the container. That's got to be a gas. Because when you put a liquid in there, it maintains its own volume. It may not fill the container. So the second one's a gas. So that would be B, solids, gases. Is this too elementary? Okay. Just check it. How many times larger in size is the atmosphere pressure unit than the millimeter mercury pressure unit? Well, I would look at it. They're related, right? 1 atmosphere is how many millimeters of mercury? 760. So that's another way of saying, what's the ratio? It's 760 to 1. They're trying to be tricky, I think. All right. Number 4. Indicate what the missing words are in the following statements of Charles' law. What is Charles' law? Something's constant. Right? Oh, yeah, you're right. You have these 4 conditions, right? Okay. So in Charles' law, that one's constant. You're right. Moles is constant. So that means this is a relationship between volume and temperature. So now we just have to find one that fits. Let's see. The volume of the gas sample is proportional to its is inversely proportional. No, directly proportional, right? Because if this one goes up, that one has to go up to keep this one constant. So directly is the first one, so it's got to be this one or this one. And then the temperature has to be Kelvin. Because we can't tolerate negative numbers. And Kelvin starts at 0. All right. I'll be willing to bet somebody has thought of negative Kelvin, just so I could write a dissertation on it. We'll get a publication out of it. Okay, 5 and 6. Looks like we got both of them there. So 5, the correct form of the equation for the ideal gas law. Right. We normally see it this way. P times V equals moles times gas constant times temperature. So that was pretty simple. Right there. How about number 6? What's the volume in liters occupied by 2.12 moles of nitrogen gas? That may or may not be relevant. At 0 atmosphere, that's pressure, 0.745 atmospheres, and a temperature of 55 degrees Celsius. And the question is, what's the volume? So we extract stuff from that problem and put it up here in a more recognizable form. We know that this one, if we're going to solve for that one, is this a state function or a before and after? It's a state. We don't know how it got there. These are just conditions as it is right now. So that means we have to use the ideal gas equation. Solve it for V. nRT over P. And that means we need, let's see if I got enough forward space here. V is going to be equal to number of moles. I'm going to leave out the units. Just take up less space. R, 0.08206. All right, that should be useful information at the back of your test, in case you're wondering. Temperature. Okay, we have to add 273 to this one. So temperature is going to be, let's see, 8 here, 2 here, and 3 there. Okay. Yep. And then pressure. Atmospheres, 0.745. Right? Now we know the units are correct because the units are determined by the constant, this one right here, which is liter atmospheres per mole K. So that tells you the units that you need here. If you have a different value here with different units, then these have to be converted to match those units. Right? So liters volume, that's going to be our answer. Atmospheres here, moles here, and K there. So we got all our units matching. Now we just need to get out the calculator, see what the answer is. That's the thinking part. The rest is just crunching numbers. Let's see, 0.08206, 328, and 0.745 if I transpose my numbers correctly. 70, let's see, 3. Let's pick the best answer. Round it off to 3. Significant variance, 76.6 liters, which is C. Right? As it turns out, doesn't matter what the gas is. For this type of problem, could have been helium, could have been carbon dioxide for all we care. We get this exact same answer. There we go, 7. The partial pressure of helium in a gaseous mixture of helium and nitrogen trifluoride. Those are the two gases. Is the pressure, the partial pressure of helium. So we want to know this one. The pressure that the helium would exert in the absence of the nitrogen trifluoride. We found our answer. That's the definition of partial pressure. It's the pressure that helium exerts even if nitrogen trifluoride were absent. And then when you get nitrogen trifluoride in there, then the total pressure is just both of them together. That's Dalton's law of partial pressures. We don't have to waste time on the rest of them. We found our answer. And there are no squirrely ones down there, like none of the above, 2 of the above, that kind of stuff. If that's the case, then you just go down until you find the right answer and stop. Test taking technique. All right. Yeah, that was kind of squirrely. Let's scroll it a little bit. 10. It's not going to be enough. Let's go back up. There. Number 9. Which of the following is not a factor in determining the magnitude of the vapor pressure of a liquid? Not a factor. We're looking for the vapor pressure of a liquid. The temperature of a liquid, that have an effect? Yep. So A is true. What about B? The strength of the attractive forces between molecules of the liquid. Yep. The weaker the attraction, the higher the vapor pressure. Okay. How about C? The size of the container for the liquid. Okay. That one's out. So C is the answer. It's the one that's not. And just to be thorough, the type of forces between molecules within the liquid, yeah, that has a bearing. Okay. How about number 10? A liquid is placed in a closed container. Equilibrium is reached when all the liquid evaporates. What do we need for equilibrium? Right? Got to have our liquid here. Got to have a headspace. And we got to seal it off in order to reach equilibrium. If it's not sealed off, and it'll just keep evaporating until it's all gone. But we're making vapor in the beginning, and then once we get enough vapor molecules up here, we start recondensing. And when these rates balance, then you have equilibrium. So if all your liquid's gone, there's no way you can have equilibrium. Right? If you just put a little bit of liquid in there and it all evaporates to fill the space, it just turns to vapor. There's no exchange between liquid and gas. So that's why the first one is incorrect. When the rate of condensation equals the rate of evaporation, there you go. B is your answer. That last one, when molecules cease to pass from liquid to vapor, that never happens. As long as there's liquid in there, there's evaporation. And at equilibrium, you also get condensation. That's the microscopic level activity. It's always evaporating and always condensing. We don't say always too much or too often in sciences, but occasionally it's appropriate. Let's see. Here we go. 11. Liquids will boil at lower temperatures at higher elevations because. Now, first of all, is that true? Can you boil a liquid? Let's just be specific. Can you boil water at a higher elevation when the temperature is lower? You ever try to boil water in Denver, say?
I don't think you can.
Yeah, you can.
You can?
Yeah.
Oh, that's weird, but.
It's a mile high.
Okay. Yeah, I get cool.
We're not trying to snow you. Water will boil at a lower temperature at higher elevation. Why? Because its equilibrium pressure is lower. Because the atmospheric pressure is lower at higher elevation. Then it will boil at a lower temperature. It vaporizes with lower energy. So at lower temperature, you can boil water. So let's see. I may have touched on the answer already. Why is that? The intermolecular attractions are weaker? No, they don't change at all. The attractions don't change. That's intrinsic to the liquid. Atmospheric pressure increases, not decreases. It's harder to transfer heat to the liquid. I don't see how that's valid. I mean, you put it on the same stove, whether you're at sea level or you're in Denver. The vapor pressure at which boiling occurs is lower. That's your trick right there. Vapor pressure that at which the liquid boils. So that's why it takes longer to cook an egg, to boil an egg in Denver than it does in Beckley. or in Savannah, Georgia, for that matter, at sea level. Because you can't get the water hot enough, right? When the water starts boiling, that temperature is constant until all the water's gone, right? So as you heat the water up, the energy you put into it goes into exciting the molecules. But once it starts boiling, the energy now is used exclusively to vaporize the water. You've reached a point where you're breaking the bonds between the water molecules. So if you diagram that, and let's see, temperature, and this is time. Then if you start off at a solid here, then as you heat the solid up, does that. And when it melts, it stays at that temperature until it's all gone, until it's all liquid. And then it heats up again. And then it starts to boil, it stays at that temperature until it's all gone. So it's in the vapor phase. And then you can heat the vapor up even further. Right? So you got solid exclusively here. You got the beginnings of liquid here and the beginnings of gas here. And in here, you've got both solid and liquid. And here you have liquid and, excuse me. Yeah, that's right. Solid, liquid here, liquid only there, liquid and gas here, and exclusively gas there. That's characteristic of any heating curve for a substance as it changes phase. So that's why if you want constant temperature, say if Robert Boyle wanted constant temperature when he was doing his pressure volume experiments, he could have taken his J tubes and submerged them in ice water. And that would have been a constant temperature. As long as there's solid ice and liquid water, when they reach equilibrium, it's going to be 0 degrees until all the solid's gone. As long as you got both of them in there, it's a constant temperature. Okay, 12. Which of the following statements about intermolecular forces is incorrect? They must be overcome in order for molecules to escape from the liquid state into the vapor state. Yeah. Those forces that are holding the molecules together, you got to break those bonds before they can leave the liquid and go into vapor. So A is true. How about B? They're much weaker than intramolecular forces. What do we mean by intramolecular? What's holding the molecule together? Right? So the intermolecular forces must be weaker than the intermolecular, not the intramolecular. Inter, between molecules, is weaker than intra, within molecules. And I mean, it's pure logic. If it was the other way around, if intermolecular forces were higher than intra, they just rip the molecules apart. So B is true. How about C? They are electrostatic in origin. Yeah, I'll go for that. Now, they don't have to be complete ions. You don't have to transfer electrons completely from one side to the other. It can be a slight redistribution of electron density like we do for water, right? So you get polar bond there, a polar bond there, and they don't balance each other because it's not linear, right? So you get an overall polarity that way. But it's not a charge. It's a slight redistribution. So you're going to have a slight negative here and a slight positive there. So, but it's still electrostatic. It's still a difference in electric charge. So C is true. How about D? They occur within molecules rather than between. That's false. Intermolecular forces are between molecules. It's like how we name sports. Intramural sports between schools. Intramural sports are A team battling B team. It's the same school. Okay, let's see. I'm going to have to down here and scroll it. That's good enough. Okay, 13. In which of the following liquids would London forces be the predominant intermolecular force? London, the full name, dispersion forces. So when do London forces occur? One word and starts with an A. Always. London dispersion forces are always there. It's the balance, right? Are there other forces that are stronger than London? In which case you can pretty much discard and not even consider London forces because they're so weak. So if there are other forces like if there's polarity among the molecules, if there are ions, then you can discount London forces because they're so weak. So what you need is to have a predominant intermolecular force that's based upon London. You need to have molecules that are nonpolar. Then you would see the effect of London forces. So we look for polarity. Right? A, H, C, N. Yep, that's polar. Right, so that one overwhelms the London forces. How about the next one? Dinitrogen. That's a good one. Right, that's nonpolar, definitely nonpolar. H2S, that's polar. We found our answer actually. Sulfur is kind of like water. It's polar. And IF, iodine and fluorine. So which way is the polarity on this one? Remember electronegativity? Which one's the most electronegative? Fluorine. Fluorine is the most electronegative element in the periodic table. That's why when fluorine combines with other atoms in covalent bonds, they're very, very stable. Anyway, we found our answer is B, nitrogen. Now, how do we know that it's only London forces? I mean, we can theoretically say they're right. It's nonpolar, so we don't have any polar activity. Right. We look at the boiling point. What's the boiling point of nitrogen? It's pretty cold. You got to get it really, really cold so that the kinetic energy, the dispersive forces are decreased to a point where the London attractions can overcome and condense it into a liquid. Right? If it's got any kinetic energy at all, it's going to be a gas. That's how we know. All right, let's page up. Well, I might as well while I'm here. Just scroll it and get both of them. Go. That one out of the way. 14. How many things do I have? Not spending too much time. Okay, I think we'll be all right. Number 14. Which of the following descriptions apply to matter in the solid state? Well, let's see, a solid has a definite shape, right? Definite shape, definite volume. Both of them. So anything's match here. Definite shape. Oh, they're talking density too. We got more. Okay. I need to go deeper. Definite shape, yes. High density? Yep. High density. So A is true. Right. Cohesive forces dominate over disruptive forces. Yep, that's true. Otherwise, it wouldn't be a definite shape and definite volume. How about C? Kinetic energy dominates over potential. Nope. Kinetic is disruptive. So potential energy dominates in a solid. So D is more than one correct? Yep. D is no correct responses. That didn't work because these two are correct. So D's the answer. All right, 15. Which of the following samples of gas would have a new volume of 3 liters if the pressure is decreased from 3 to 1 atmosphere? Okay, this is a before and after, correct? And we're looking at volume and pressure. So pressure times volume before equals pressure times volume after. Okay, so what's before? Which of the following samples would have a new volume of 3 liters? So the new volume would be 3 liters. Right, that's the new volume. If the pressure is decreased from 3 atmospheres to 1 atmosphere. So it goes from 3 here to 1 here. And we're solving for this one. So this one will be 3 divided by 3 is 1, right? So the volume would be 1 liter of something. The only one that's got 1 liter is helium. Okay. You can reason it out too, but I thought calculating it might. Well, it's just one way of doing it. Okay. 16. Which of the following is a correct equation for the combined gas law? Remember the combined law? PV over NT. There's 1, 1, 1, 1, and then PV over NT, 2, 2, 2, 2. All right. So it looks like it's solved. The A is solved for pressure, B is for volume, C is for temperature. So let's solve each one. It looks like we're solving for P2, B2, and T2. All right, so A should be solved for P2. So P2 is going to be P1, V1. Let's see. Keep this one here. Put this one down underneath. Put these two on top, along with this one. Into T2. These two go over here. And this one goes down here with N1 to T1. Okay. So it's saying, oh, all right. What else is it saying? I don't see any moles in here at all. So it's saying the mole stays the same. So we would just eliminate the moles and see now does it match. P1, V1, T2. Nope, A is wrong. The way they have it is wrong. How about the next one? Solve for V2. Okay, so we're going to solve for this one. We need P1, V1, and we're going to leave out the moles, right? Okay, so if we're solving for this one, that means P1, V1, T2, and then T1 and P2. So P1, no. Their answer is wrong. Doesn't match my answer. How about solving for T? T2. Okay, solve for T2. All right, T2 has got to go over on this side. That means we keep this one and this one here. Throw out the moles. And T1 has to come back over here, this side. And then P1 and V1 have to come over on this side. There we go. So T1's there, P2's there. It's got the wrong volume. Right, so that one's wrong also. There are no correct responses here. Okay. Let's see, I'm going to have to scroll. That's good. 17. When the vapor pressure of a liquid equals atmospheric pressure, the temperature of the liquid equals what? When the vapor pressure of the liquid is equal to atmospheric pressure, what's it doing? It's boiling. When the vapor pressure equals the atmospheric pressure, you're at boiling. The temperature of the liquid equals, well, it equals 100 degrees if you're at, if you're talking about water, but it doesn't say water, it just says a liquid, right? So we don't know what the temperature is. So A's false. Boiling point is boiling point of the liquid. When the vapor pressure of the liquid equals temperature, well, that's right. It's a boiling point. The normal boiling point of the liquid. Okay. So here's a case of picking the best answer. Yeah, it is the boiling point. But a better answer is it's a normal boiling point. Because it's based upon atmospheric pressure. That's the kicker right there. Normal. Okay. That'll mess you up if you're not paying attention. All right, so let's go 17, 18. Let's go ahead and scroll. Oh, too far. There we go. 18. Intermolecular forces differ from intramolecular forces in that, okay, we've got multiple selections down here. They occur only in liquids? No. You can get intermolecular forces in solids and gases. They're just different in magnitude. They are much stronger. Intermolecular are weaker than intramolecular. They occur only when hydrogen atoms are present. Sorry, no. They're alluding to hydrogen bonding here. More than one correct? Nope. There are no correct answers. None of those are right. 19. In which of the following pairs of molecules would the first listed member of the pair have a higher boiling point than the second listed pair? Okay. So let's see, how about A? So what are we talking about? If it's got a higher boiling point, we need stronger intermolecular forces in the first one than in the second one. So if you look at this one versus this one, which one has the stronger polarity? That one. Because fluorine is more electronegative than bromine. So this one would have the higher boiling point. And A is a correct answer. How about B? Right, because we have multiple selections down here. This one and this one. Okay, these are going to be nonpolar. But here we're looking at, well, since they're both nonpolar, right, they're like this, that. So we know they're nonpolar. So the only forces they have available to them are London dispersion forces. Okay. How do we know London dispersion forces are distributed in a molecule or in an atom for that matter? The bigger the atom or the molecule, the larger the London dispersion forces. Why? Because you have more volume over which you can spread your electrons. So with the bigger molecule, this one's going to be the higher boiling point. And we find out that that's true. And as you look at the noble gases, you see that the boiling point increases from helium, neon, argon, krypton, xenon. Boiling point increases steadily as you go down. That means that as they get bigger, the London dispersion forces increase. That's the only thing these guys have available to them because they're single atoms. So we know that trend is true, and we're extending that concept to molecules. The bigger the molecule. We also see that in hydrocarbons, where you carbon and hydrogen only. We have methane is just one carbon. Methane is 2 carbons. Propane is 3 carbons. Butane is 4. As you add more carbons and the hydrogens that go around them, their boiling points increase until you get to the point where it's hard to boil them. Now you're talking about melting point. When you get to, let's see, octane is still a liquid. It's in your gas tank. Then nonane and decane. Now you're starting to get liquefied at room temperature. Talking about diesel fuel. And the boiling point, melting point, you go on up until you get to asphalt. Like maybe 14 or 15 carbons and above, you get into asphalt. And it just gets thicker and thicker and thicker because the London dispersion forces are available. More of them are available for each molecule. Okay, so that one doesn't work because the first one's not the highest. C, oxygen and NO. Okay, this one's going to have London dispersion. This one's going to be polar. So the boiling point here is going to be higher. So that one doesn't work. D, more than one correct answer? No. No correct answer? No. We found an answer. It's A. The first one in the group has the higher boiling point, just like the problem. Sometimes I have to go back and reread the question. I get so wrapped up in thinking about individuals that I lose track of what the question was. All right, so let's page it up. There we go. 20. Oh, everybody's favorite. We got 3 statements, and we have to decide which are true, which are false, and then say down here, all 3 are true, 2 are true, only 1 is true, none are true. So we got to look at each one. Sublimation and deposition are opposite changes of state. Okay, what's sublimation? Solid to gas. That's sublimation. Deposition. Gas to solid. Number one is true. They're opposites of each other. Number two, a pressure of 1 atmosphere is greater in magnitude than a pressure of 720 torr. Now, 1 atmosphere is 760. So 1 atmosphere is greater than 720. 2 is true. 3, the boiling point of a liquid can be increased by heating the liquid to a higher temperature. The boiling point is determined by the liquid and the external pressure. Heating it to a higher temperature doesn't change the boiling point. So 3 is false. So 1 and 2, 2 of the 3 are true. That's B. Okay. I generally don't put too many of these types in the exam because they take so long to deal with. But you got to look at each one individually and then make a decision. So I tend to move these into extra credit region. In fact, I think that's where, for this exam, that's where all of them are. They're in extra credit.
On the last one too. That's good.
Yeah. Oops. Oh, there's another one. Okay. Let's put it down below the horizon. There we go. And another one. Associated with Charles' law is the concept that if the temperature of the gas increases, the volume of the gas also increases. Temperature, volume, yeah, that's Charles' law. That's true. Liquids show little change in volume with changes in temperature.
Yeah.
That's true. They do change in volume, but very little. So technically, we could say that was true also. Dipole-dipole interactions are examples of intramolecular forces. No, intermolecular forces. You can stop there. That's false. Right. So it's 2 of them. That means B. Okay. Let's see, I should be able to page to the next one. Here we go. Let's see. 1, both dipole-dipole interactions and hydrogen bonds are stronger than most single covalent bonds. That is false. Dipole-dipole and hydrogen bonds are between molecules, whereas covalent bonds are inside the molecule. They are always bigger, stronger. The value of the ideal gas constant is the same for all gases under ordinary conditions of pressure, volume, and temperature. Yep. I left out moles, but I'd say that's true. Both condensation and freezing are endothermic changes of state. Let's see, condensation goes from, let's see, condensation is gas to liquid, right? Okay, so when you go from gas to liquid, you're losing energy. That's exothermic. Okay, and the other one is, oh, that's as far as we need to go. If condensation is exothermic, then it doesn't meet that condition. So we can stop there. So only one of them is true. C would be the correct answer for this one. And skip that one, and we've got another one coming up here. Let's move down here and scroll it. It's almost quicker to go over there and do it by hand. Do it at the computer. 25. Number 1. Water's boiling point is much lower than expected based on comparison with other substances because of hydrogen bonding. Is the boiling point of water lower than expected? No, it's higher than expected. In the gaseous state, disruptive forces and cohesive forces are about the same magnitude. Oh, disruptive is dominant in gases. 3, as liquid surface area increases, the rate of evaporation of the liquid increases because molecules encounter less external pressure. No. It does, the rate of evaporation does increase, but it's not because of less pressure. Pressure is a intensive property. Right? It doesn't matter how big the surface area, the pressure is going to be the same. So the rate of evaporation increases because you have more surface area in contact with the vapor phase. Right? So that was false also. So the answer to this one's D. None of them are true. (26) For each of the physical state characterizations, select from the response list the physical state or states to which the characterizations apply. Oh, okay. So which one, A through D, applies to indefinite shape? Shape. Indefinite. Indefinite shape is, well, it has to be a gas. That's the only possibility. Oh, no, excuse me. And liquid. Yeah, liquid needs a container. Gas needs a container. So D is the answer to that. Yeah, while we're here, how about 27? Definite volume. Definite volume would be solids and liquids, right? Yeah, liquids and solids both for that. I don't have it marked, but I figure while we're here, let's see. Let's scroll this one up a little bit. Go. 28. For each of the physical state key, potential energy dominates over kinetic energy. Okay. For gases, kinetic dominates. For liquids, they're about equal. And for solids, the potential is greater than kinetic. So we're looking at solid state. Okay, let's see if I can scroll this one a little bit. Get them both up there at the same time. Go. 29. For each of we're still on that mode. Particles are relatively close together. That's true for both solids and liquids. So the answer is C. Gases, they're way, way, way far apart. That's why in certain cases, for all the gas laws, it doesn't matter what the gas is because they behave as if they're all the same. There's so much space between them. The size of the particles and the interaction between them is minimal. Can be ignored, actually. Consider the mathematical expression for gas laws listed. Select the correct name for the law. P1V1 equals P2V2. Boyle. This is somebody's mouth moving. Boyle's law, B. All right. For this expression, which one is this? Volume and temperature, that's Charles' law. (34) Select the name of the change of state for when energy is absorbed. Energy is absorbed for, let's see, we've got to go from either solid to gas, solid to liquid, liquid to gas, or solid to gas for energy to be absorbed. You got to spread those molecules further apart, give more energy. So you need, let's see, the first one would be melting. And then liquid would be boiling or vaporization. And from solid to gas would be sublimation. Oh, we only have one selection. Condensation doesn't work, deposition doesn't work, freezing doesn't work, sublimation. So A is the answer. (36) Characterize the effect the changes will have on the vapor pressure and boiling point of a liquid by decreasing the temperature of the liquid by 20 degrees at constant pressure. Okay, so we want to characterize the effect on the vapor pressure and boiling point of a liquid by decreasing the temperature of the liquid by 20 degrees. So the change in temperature is going to be minus 20 degrees C. What effect does that have on these guys? And the external pressure is constant. Okay. Vapor pressure decreases. If we decrease the boiling point, if we decrease, what effect does this have on the boiling point? Well, the boiling point doesn't change. Boiling point is characteristic of the liquid under certain pressures. So the boiling point doesn't change, it's constant. Okay, so that in that case, we could say boiling point does not change, boiling point doesn't change. So it's got to be B or C. So what effect does it have on the vapor pressure? Right? The vapor pressure, if you decrease the temperature, the vapor pressure is going to decrease because you're cooling the liquid. It's got less energy to escape into the vapor phase. So this will decrease. So that means B is the answer. Okay. All right, 36. 38. All right, it's all there. For the following intermolecular force descriptions, select the correct name from the response list. Permanent electrostatic interaction between polar molecules in which no hydrogen is present. Electrostatic interaction. And it's permanent. Right? So that lets out London. London is intermittent. Permanent is between polar molecules, electrostatic between polar molecules in which no hydrogen is present. Okay, so you've got a dipole-dipole interaction, not hydrogen bonding. So that is here. Covalent bond is not an intermolecular force, so we throw that one out. We threw London out. Hydrogen's thrown out because there's no hydrogen present. It says so right there. So this is the only one left. It's a dipole-dipole interaction. Okay. Let's get down here and scroll a little bit. Go. 40. A solution may contain what? Let's see. Solutions are made up of solvent, solute. How many can you have of each one? You can only have one here. One solvent and as many solutes as you want. So let's see which one matches that. only one solvent and many solutes. There it is. Now, may contain only one solvent and one solute, but A is a better answer because you can have many solutes. Now, that doesn't mean that the solutes don't interact when they're in solution. They do interact with each other. But this is based purely upon the relative amounts. Right. We call the solvent one that's the majority. 41. Which of the following statements concerning a saturated solution is incorrect? Saturated solution. Okay. Undissolved solute must be present. Well, first of all, saturated solution is what? Maximum amount of solute. Okay, so that can occur. You don't have to have any undissolved solute to do that. You can be right at saturation for a given temperature, and it'll still be saturated. Now, if you do have some undissolved solute in the bottom of your container, then that's guaranteed it's saturated, but it's not required. So undissolved solute must be present? No, not necessarily. Undissolved solute may or may not be present. Yeah. Oh, wait a minute. Incorrect. Read my question again. So this is correct. Undissolved solute, if present, is continually dissolving. Yes, that's true. But it's also being replaced. It's going into solution, coming out of solution at the same time. Undissolved solute, if present, is in equilibrium with the dissolved solute. That's true also. Okay, so the one that's incorrect is this one. Must, that's the key word, must be present. If it said may be present, then it would be the same as B. So A is the answer because it's wrong. Okay, there's 43, peeking it out the bottom. Let's go down here and scroll it. Okay. 43. For which of the following types of ionic compounds are most examples insoluble in water? So you would need to look at your diagram, which will be available on the exam too. And it's got the boxes with the clear and the gray things, but it's also got the rules at the bottom. So if you look at the rules, you find that which are insoluble in water. Nitrates are all soluble. Sulfates, most examples insoluble. Most sulfates are soluble. There are some insolubles. Hydroxides. All right. Hydroxides are mostly insoluble, except for the alkali metal hydroxides. Right. That's rule number one. Rule number one trumps this rule because it's above. Remember that relationship? The top of the rules is preferred over any down the bottom. So if you have a conflict, the one above wins. So the alkali metal hydroxides are soluble, like sodium hydroxide, potassium hydroxide, lithium hydroxide, any of those. They're all soluble. But the rest of them, all the other hydroxides are insoluble, like magnesium hydroxide, calcium hydroxide, aluminum hydroxide is insoluble. Most of those are insoluble. Most of the chlorides are soluble, with a few exceptions. Silver chloride, we dealt with that one already. There are some others. Okay, So the answer to this one is C. '45. What is the molarity of a solution containing 16.7 grams, 7 grams of ammonia in 1.5 liter of solution? Can't do it with that value. We need to know moles. 16.7 grams. Right. So that's how many moles of ammonia we have. Let's see. Nitrogen is 14.01. 3 hydrogens are 3.03. 1704. To give us the moles of ammonia. 16.7 and 17.04. So that's 0.980. 0.980 moles. Now we can calculate the molarity. So the molarity is moles per liter. 0.980 divided by 1.5 is 0.65 molar. That's rounded off. 653. And that makes it this one right here. Okay. So it's a two-step process. All right, 46. Let's go ahead and scroll this a little bit. Ooh, can I make it? Let's see, 46. In 145 milliliters of 2 molar KOH. So volume equals 145 milliliters. And molarity is 2.00 molar of KOH. Diluted to 1.5 liter volume. So this is the concentrated, dilute. So we're going to dilute it to 1.15 liters. And we want to know the resulting solution contains how many moles? Oh, blue smoke. How many moles does the resulting solution contain? Contains the same number of moles we started with. We're going to dilute it. The moles here equals the moles there. So we don't need to do that calculation. We just need to find out how many moles there are. Well, let's see. Molarity times liters. So 2 times 0.145 is the number of moles. So 0.290 moles. So that answer is A. Okay. So it gave us all this information, a lot of information we didn't even need. Ooh, 7. A colloidal dispersion differs from a suspension in that colloidal particles, what? Colloidal particles don't settle. It's not a solution because the particles are suspended not by filling in holes in the solvent, but by the kinetic energy delivered to the individual particles from the moving molecules in the dispersing medium. So it's a different mechanism. But the particles are small enough, have low enough mass, so that kinetic energy delivered by this dispersing medium can keep them suspended. Whereas a suspension will settle. There's not enough energy in there to keep it suspended. So let's see, which one does that match? Colloidal particles a colloidal dispersion differs from a suspension in that colloidal particles tend to settle at an appreciable rate. No, colloidal particles don't settle. Are large enough to scatter light. Well, yeah. Are large enough to be seen? No, can't see them with the naked eye necessarily. Are large enough to be seen with a microscope? Yeah, maybe. Best answer is large enough to scatter light, but the particles in a suspension will scatter light too. Right? Just mix sand and water and shine light through it. Actually, it's opaque. So that's not a good question, is it? The best answer is B. I would say this word right here should be changed for a better question. Colloidal dispersion differs from a solution in that. That would be the better question. I'm going to make myself a note on that. This one should be a solution. To make it a better question. Okay, 48. Compared to pure water, a 1 molar sugar water solution will have what? Vapor pressure. Will it have a lower vapor pressure? Yep. It'll have a lower vapor pressure. So that means it could be A, it could be C, it could be D. B is out. It doesn't have a higher vapor pressure. So it looks like there's an explanation or an additional condition. Lower boiling point. Oops. Must have clicked the wrong button. So what effect does this have on the boiling point? Yeah, it increases the boiling point. So let's see. Lower vapor pressure, higher boiling point. So it's got to be this one. And lower freezing point. Yep, is C. Right. Boiling point elevation, freezing point depression when you put a solute in solution. All righty. That thing out of the way. 49. What is the freezing point for a solution containing 1 mole of sodium chloride dissolved in 1 kilogram of water? So the mass of the solvent is 1 kilogram. What is the freezing point for a solution containing? Okay, there's not enough information there. What else do we need to know? Okay. This is freezing point depression is equal to what? We need the constant. Okay. Constant for boiling point constant. We need the molality, right? What else do we need? We need the Van Hoff correction. Because when sodium chloride goes into solution, it breaks apart into 2 parts. So this is going to be 2. The molality is going to be 1, right? 1 mole per kilogram. And then the K, we're not given. So if that happens, be sure and ask me for it. I think it's 1.86. So a change in freezing point is 1.86 depression, which means it's minus 1.86 degrees C, right? Because 0 degrees for pure water. So we're depressing the freezing point by this amount. Oh, excuse me. I forgot to multiply by 2. Let's see. 16, 17, 3. 3.72. Minus 3.72. I need to make a note on that one too. K equals what? All right, that's 49. 50. Crenation of red blood cells occurs when the cells are placed in what? What is crenation anyway? Well, blood cells look like this normally, right? Crenation is going to be if they shrivel up. So how would that happen? Is if the solution outside the cell is hypertonic. It's a higher concentration of solute, lower concentration of water, so the water moves out. So we need a hypertonic solution right here to do that. '51. Which of the following solutions is hypertonic with respect to blood? Well, general physiologic concentration is hypertonic, higher concentration. 0.5%, 0.7, what is isotonic? 0.9% sodium chloride will be isotonic. In fact, in your lab, you're going to make one of those solutions. You're going to make a 0.9%, you're going to make a, I think it's 20%. Very hypertonic. Okay, so A and B can be it. So what's our other? Remember D5W? Dextrose 5% by weight. So 5% dextrose would be isotonic. So we need something higher concentration than that. And that's this one. Okay. Every EMT knows that one. 52. Are we getting close to the end?
On page 14, 23.
14. Lunch, because
Yes.
I don't want to eat up your lab time if I can help it. Okay, which of the following statements about solutions is correct? Solution is homogeneous mixture. Yeah, that's true. It is possible to have solutions in which both solute and solvent are solids. Yep, like brass, copper and nickel. How about C? Solutions readily separate into solute and solvent if left undisturbed for 24 hours. Nope. So 2 of the above are correct. More than one is correct, D. 53. A crystal of solid sodium chloride is placed into an aqueous sodium chloride solution. Okay. So we've got a solution down here that's aqueous sodium chloride, and we're going to put into it crystal of sodium chloride, solid. It's observed that most, but not all, of the crystal dissolves. Right? So if we wait long enough, we still have some of this left over at some point. This means the original solution was, if some of this dissolved, that solution is not saturated yet. It's unsaturated. Right? It's not supersaturated, it's unsaturated. We don't know whether it's dilute. It's probably not dilute because when you put that crystal in there, it reaches saturation without using it all up. If it were very dilute, it probably dissolve all of it. So it's sort of you have to make an assumption. So the best answer is unsaturated. #54. Consider the following substances and their polarities. Okay. A is polar, B is polar, C is nonpolar, and D is nonpolar. Okay. It is true that A is more soluble in C than in B. A is more soluble in C than in B. A is false. Like dissolves like, correct? Okay, C is more soluble in D than in A. True. D is more soluble in B than in C. False. And D, more than one correct response? Nope. No correct. We do have a correct one, B. B is the right answer for that. #55. In which of the following sets of ionic compounds are all members of the set insoluble in water? Okay, so we might have to use our table. I should be able to figure this one out. All right, silver chloride is insoluble. You say all members are insoluble. Lead 2 chloride is insoluble, but ammonium chloride is soluble. All ammonium salts are soluble. So A is not it. B, insoluble. Copper carbonate, calcium carbonate, magnesium, all carbonates are insoluble, except for the alkali metals. Sodium carbonate, potassium carbonate, those are all soluble. Right, for the same reason as the hydroxides, because all alkaline metals are soluble. No exceptions, right? So that was true. Those are insoluble. Lead sulfate, iron sulfate, barium sulfate. Insoluble. Lead 2 sulfate. Iron 2 sulfate. Barium sulfate. Barium sulfate is insoluble. Lead, I think iron sulfate is, oops, not there. Okay, we need a copy of our chart. Here it is. Iron 2 sulfate is soluble. I thought that's right. This one is soluble. That one's insoluble, that one's insoluble. So B is the only right answer. That was kind of tricky. 61. Which of the following solutions has an osmolarity of 3.0? Osmolarity. I don't think they have an abbreviation for this one, like a big M for molarity. Osmolarity, you have to write the whole thing out. That's cheating. Osmolarity of 3. Okay. So if it's non-dissociated, if I equals 1, then the value should be exactly equal. right? But there's no 3s in here. And so it can't be that. It's not this one. This one would be a 4 osmole. And this one would be 1, 2, 3, 4 times that is 4 osmole. So there are no right answers. They're all wrong. Take care of that one. 62. In which of the following pairings are the terms closely related? Hemolysis, hypotonic solution. So what happens in hemolysis? The external solution is hypotonic, so water moves into the cell and blows it up. So A is correct. How about B? Hypertonic, higher osmotic pressure than within the cell. Yep, that one's true. Isotonic solution, crenation. Nope. Isotonic is perfect. More than one correct response, yeah. The easy answer. Uh, 63, I'm gonna have to scroll this one. Let's see. It's one of those that everybody loves. 63. Okay, so we're going to look at one. Equal volumes of two solutions of the same molarity contain the same number of grams of solute. They contain the same number of moles. Now, the only way they can obtain the same number of grams is if they're exactly the same molar mass. We're not told that. So we can't say that one is true. We have to say that one is false. 2, hemolysis and crenation are opposite processes. I'll go with that. The solubility rule, like dissolves like, is not adequate for predicting the solubility of ionic compounds in water. Yeah. What happened to the answer? It's missing, isn't it? Oh, pressure. Well, let's see. We know that this one's right. How about 3? The solubility rule is not adequate for predicting the solubility of ionic compounds in water. Technically speaking, that's true. Generally speaking, there are some ionic compounds that are not soluble in water. Yeah. So this is the only true one, right? Just one of them.
If you actually go to the back page, there's an answer sheet and it says 63 feet.
2 of the 3 statements are true. Solubility, let's see. Hemolysis and crenation are opposites. Equal volumes. I know that one's false. So we must be saying that solubility rule is adequate for predicting the solubility of ionic compounds. Now, I think that answer is wrong. Because we know that under certain circumstances, just because it says like dissolves like doesn't mean it's soluble. Because we know by our rules or by the table that it's not necessarily soluble. So actually the answer should be C. $63. Yeah, reason. Here we go. 63. There we go. For posterity's sake. And 65. Starting to run out of ink here. Okay, it's another one of those. Addition of 40 milliliters of water to 10 milliliters. 10 milliliters of 8 molar sodium hydroxide would produce a 2 molar sodium hydroxide solution. And we're going to add 40 milliliters. So 10 times 8 is 8 millimoles. That's what you're starting with. Now you're going to end up with 50 milliliters. Right? 8 divided by 50 is 8 divided by 100. No, 16 divided by 100 is 0.16. All right, so 1 is false. That's not right. What about 2? Henry's law is a pressure solubility relationship for gases and liquids. That's true. Henry's law does say that. Boiling points are the basis for the solubility rule, like dissolved likes. No. So Henry's law is the only correct one. See. All right. Excuse me. Let's see. Yeah, there's nothing hiding down below. Just check it. 1. 2 liters of 6 molar solution would contain 12 moles of solute, independent of the identity of the solute. Let's see. 2 liters, 6 molar equals 12 moles. Yeah, 1's true. 2. For liquid-liquid solutions, volume of the solution is always greater than the sum of the volumes of the solute and solvent because of solvent repulsion. That's not always true. It could go the other direction. It could be a lesser volume. It could be more, it could be less. But osmotic pressure is the amount of pressure needed to prevent the process of osmosis from occurring. Yeah, that's one way of determining osmotic pressure. Right? With the 2 solutions, you have the amount of pressure required to stop the movement of water through the membrane. Okay, so 3 is true. That means B. 2 of the 3 statements are true. What happens if you artificially exceed the osmotic pressure? On the hypotonic side, you can get reverse osmosis. You can drive water back through the membrane the opposite direction. 67. For the set of ionic compounds, those 3, choose the correct characterization of their solubilities in water from the response list. Oh, okay. Sodium nitrate is soluble. Potassium nitrate is soluble. Right? And ammonium nitrate is soluble. They're all soluble. Oops. All 3 are soluble. You have 2 rules going on here. The alkali metals, soluble, all nitrates are soluble. So you're good there in both of them. Nitrates are soluble. Most ammonia compounds are soluble, but the nitrate wins. So all of these are soluble. 68. For the set of ionic compounds, choose the correct characterization of their solubilities in water for the response. So lithium chloride is soluble because lithium is an alkali metal. Silver chloride is insoluble. We know that one. Magnesium chloride is soluble Because most chlorides are soluble. There are just a couple of chlorides that are not soluble. Silver happens to be one of them. So 2 of them are soluble. B. Okay. Is that it?
Question 8.
Ah, okay. 80. That's good because I'm running out of ink. Using the response list, characterize the osmotic pressure for a 0.80% mass volume magnesium fluoride with respect to cells. Okay. This, remember, 0.9% sodium chloride is isotonic. So we need something that's close to this. Or what's the relationship of this one to this one, right? Is this more concentrated than that one? Well, yeah, because 2 ions here would be relative to 1.8% ions. And this, I'm just estimating. Here you've got 3. So that's 2.4. So I would say that this one is hypertonic. Okay. And that should be it, right?